This is just a definition, okay? So now notice some things. X, if I take the Hermitian conjugate of X, we see that it's a Hermitian matrix, right? Because the Pauli matrices are all Hermitian matrices, and X, Y, and Z are real numbers. Okay, so this is number one. Number two is that if I look at the determinant of X of R, what do I get? I get minus, within brackets, X squared plus Y squared plus Z squared. In other words, the determinant of X gives me the minus mod squared of the vector R. Okay, is this clear?
Yes, sir.
Okay, so now, let's make a rotation. Let's rotate the vector R by some rotation matrix big R. So we go from R to R prime, where R prime is given by big R acting on R. Okay? And then ask the question, what is X of R prime and how is it related to X of R? So according to the definition of X, X of R prime is given by X prime sigma 1, Y prime sigma 2, plus Z prime sigma 3. Right? Is this clear? I'm just using the definition of X.
X prime, Y prime, and Z prime are the components of R prime.
Exactly, yeah. Okay. Now there must be some relationship between, some transformation between, this X of R, and X of R prime as well, which corresponds to this rotation, right? There should be some sort of continuous so if R is small, then in some sense X of R prime would be a small matrix which is very close to X of R. But if R is a big rotation, then X of R prime should be a matrix which is quite, in some sense, quite distant from X of R. Okay. So what I'm saying is that X of R prime is X of R acting on R, right? And I want to know, how is this related to X of R? Because if I can do that, then we shall see that this will allow us to crack the homomorphism, okay? So to do this, let's go back and look at the relevant properties of X of R. One is that X of R is Hermitian. The other one is that its determinant gives me the length of the vector squared. So this transformation that takes us from X of R to X of R prime should preserve these, these properties, right? I mean, this is obviously also a Hermitian matrix. So, because both X of R and X of R prime are Hermitian matrices, if they're going to be related somehow, then that relationship has to be in this form. Okay? Because it's only, so if X of R is Hermitian, then this relationship guarantees that X of R prime is also Hermitian. If on the other hand, if you say, okay, why don't I try this? X of R prime is some matrix U. U is some matrix. We don't know what matrix it is. Times X of R. This will not do, because if you take the Hermitian conjugate of this, you will not get a Hermitian matrix over here. Whereas if I take the Hermitian conjugate of this thing, what do I get? If I get U X of R, U dagger, Hermitian conjugated, then I get U dagger, dagger, X of R, dagger, U of dagger, but U dagger, dagger is U, X of R, U dagger, which is exactly X of R prime, right? So, and here we have X of R prime dagger. So we see that X of R, by postulating that X of R is related to X of R prime in this fashion, we guarantee that both of these things are Hermitian. Okay?
Is U here unitary?
Not yet. It will be soon. Yeah. So another thing that we can notice is that this is a traceless matrix, right? So if I say, what is the trace of X of R prime, then we write this as trace of U, X of R, U dagger, right? So now if I write this, I use the cyclic property of trace, then I get U dagger U of X of R. So, this is traceless. So that means that, well, let me put it this way. If the tracelessness of this matrix implies the tracelessness of this matrix, then it must be that U dagger U is 1. And therefore, U has to be unitary. Okay, so the tracelessness guarantees that U is unitary. Okay?
I didn't get this part, actually.
Yeah, that's fine. So, the way we have defined X, if you go back, X is traceless, right?
Yes.
So X of R prime is also going to be traceless, right?
Yeah.
So, but X and X prime are related via this equation, right?
Yeah.
So if I take the trace of this equation, then for this to be traceless as a consequence of this, then this must be true.
That's the part I don't understand. Why does it have to equal 1 or identity?
Okay, in that, then this is the right-hand side is X of R. And if this is traceless, then this is traceless.
Oh, okay. I'll have to think about that a little bit.
Yeah, no, that's good. If it's some other matrix, then there is no reason for it to be traceless, right? Then we will get a contradiction. Suppose that this was not 1, but it was not proportional to 1, but some non-trivial matrix A. Then the right-hand side would become trace of A times X of R, right? But we know that by construction, this thing is 0, traceless. But, if A is some other, matrix, then it's not going to be guaranteed to be traceless. And we would have a contradiction, okay?
Oh, I see.
So this shows that U is in U2. And we can actually take U to be in SU2 because the phase part of U in this transformation actually, because the phase part is essentially of this form. So the phase part from U dagger and U, they cancel each other. So they don't really do anything. They don't really have a non-trivial action on X, right? Because it's just an identity matrix times a phase. And they cancel each other out. So we can take U to be SU2. So what does this show? This shows that any rotation on a three-dimensional vector R can be mapped to A and SU2, any rotation R can be mapped to an SU2 matrix U acting on the Hermitian matrix X of R via this via this action. Okay, so we can write this a little bit more technically, more explicitly. So X of R goes to X of R, the rotation matrix acting on R equals to this. So this is the homomorphism. We have not made it very explicit, but this is essentially the homomorphism. Okay.
The homomorphism between R and U, or more precisely SU2.
Between R and U, yeah. Okay, so before we construct this very explicitly, we can, this formula is actually has in it, we can actually construct it explicitly, which we will do in a minute, maybe after the break. I want to talk about how this gives us the geometry and the topology of SO3. Okay, so if U is in SU2, then so is minus U, right? So minus U is also in SU2. So that means that the identity matrix, the two-dimensional identity matrix is in SU2, as well as the negative of the identity matrix, right? Because this is a Hermitian, this is a unitary matrix, and it has
Sir, is it because it's 2 into 2 matrix? Because like -1 square would be like 1.
yeah, exactly. Yeah. Okay. So what we see is that what does this map do? This is a 2-to-1 map. Is a 2-to-1 map with the kernel of the map being one and -1, which is Z2. Okay.
Sir, could you please re-explain the 2-to-1-ness of this map?
Yeah. So if you replace U by -U, the left-hand side doesn't change.
Oh, okay.
Yeah. So it's a 2-to-1 map where the kernel is the group Z2. So that means that by the first isomorphism theorem, if I take SU2 and mod it out by Z2, that is isomorphic to SO3.
Sir, should we not comment about the surjectivity of this homomorphism before concluding it's homomorphic to SO3?
You mean whether or not it's onto?
Yes.
Right. I think it is onto, but let me think how I can prove that. Well, it is onto, of course, but there is always, for any rotation in R in SO3, there is a for any rotation in SO3, there will be an element in SU2, right?
Physically, I guess it's pretty simple. Can we think of it physically from the example?
Yeah, physically, that's what I'm saying, is that, if physically, are there, yeah. So, I mean, let me come back to that, because I cannot think of it's kind of almost physically clear to me, but, I can't give you a complete proof right now. So you're saying that, okay, let me think about it. So you're saying that this is SO2, SO3, and this is basically SU2, and for any rotation in SO3,
Sir, I think it will be reversed, because like it's from 2-to-1 from SU2 to SO3, so it won't be a map from this direction.
right, okay, yeah. So okay, I think the way to prove this is to do the following, is to assume that there is a non-trivial matrix in SU2, apart from 1 and -1, well, okay. Okay, let me see. So suppose that this is the part that you're covering, right? Okay, let me, Nahi, let me come back to this. Let me think about it.
Okay,
and
sir.
back to this maybe in the next lecture. Okay. But yeah, thank you for the question.